Hi, the study of single degree of freedom system is central in structural dynamics. The question now is it possible for a given structure to reduce it to a 1 degree of freedom system? And if so, how do you compute the equivalent parameters? And in which frequency band is this approximation valid? So let's take the example of the portal frame where we saw that the rigid floor can be represented by a mass and the flexible column by a stiffness. The question is, of course, what is the numerical value of this equivalent stiffness? What is the value of the equivalent mass? And to which extent is this approximation acceptable? So, meaning what is the frequency band in which you can use this simplified model. For equivalent stiffness computation, the general principle is if we consider a body with arbitrary shape, a flexible body, and we have a mass hanging from it, we have the direction of motion here of the system. We can replace the mass by a force applied at the location of the mass and in the direction of excitation and motion of the mass. By doing that, we can compute what is the resulting displacement, and the equivalent stiffness will be given by the ratio of the force applied by the resulting displacement. Let's take the example of a bar in traction. So you see here that the mass is hanging from the bar and the direction of excitation is vertical. We therefore replace the mass by a force and we will compute what is the value of the displacement. So using resistance of material, we know that the axial stress is uniform over the area and is given by the Young's modulus multiplied by the longitudinal strain, which is du over dx. By integrating this uniform stress on the surface, we find a normal force and see here the area of the section. Then, using static equilibrium at the tip of the bar, we know that the normal force must be equal to the applied force. And by integrating, we get u of x is fx over ea, where the constant after integration is 0 because u is 0 at 0. We can now look at what is the value of d by replacing x by l. So we have d is equal to f L over EA, so that F over D is equal to K, which is EA over L. We see that the stiffness is now proportional to the Young's modulus and the area, and inversely proportional to the length. Now, if the direction of motion is horizontal rather than vertical, then it is not anymore a bar in traction, but it's a beam in bending. For that, we could use the formulas of resistance of materials or just go to existing tables. In this example, the maximum displacement at the location of the force for a cantilever beam is given by PL cube over 3EI, so that P over delta is equal to 3EI over L cube. We see again that the equivalent stiffness is proportional to the Young's modulus of the beam, its inertia, but also inversely proportional to L to the power of 3 in this case. So these equivalent stiffnesses for beams can be computed using formulas from resistant materials or using tables. So this is the kind of tables for a cantilever beam. You can find them for different boundary conditions, such as here simply supported beams. Now we move to the example of the portal frame. So here we have a mass that is supported by two columns, and if we divide the problem in two, we see that it's equivalent to applying F over 2 to one of the columns. So this is not strictly a cantilever beam because at the other end here it is guided so that the rotation is 0. For that you can also find tables. So here you see a cantilever beam with a guided end and a load applied, and it says that the maximum displacement at the tip of the cantilever beam is PL cube over 12EI. So because we have two columns, the total stiffness will be 24EI over L cube. The equivalent mass is the mass of the floor, so that the first natural frequency is given by 1 over 2 pi square root of 24EI over L cube m flow. So you see that we can find with a pretty simple formula the first natural frequency of our portal frame. Now for the equivalent mass, we are usually going to use equivalent kinetic energy method, where we know that the kinetic energy of the equivalent system is 1/2 its mass times the velocity squared. Now if we consider, for example, the mass on a spring, and we now consider the spring has some mass, we would like to replace the mass of the spring by an equivalent mass at the location of the initial mass m. So we will add an additional mass ma, and the question is, what is the value of this additional mass? So we have to look at the velocity profile along the spring. So obviously it's 0 at this location. It will be maximum, so it will be v at position L at the end. And between the two, we assume that the profile is linear, so it is given by this expression. The density here is the linear density, it's the mass of the spring divided by its length. Now we can just compute the kinetic energy of the spring by integrating from 0 to L 1/2 times rho times the velocity squared, which is given here. And if we perform this integration, we see that we end up with simplification here to 1/2 ms3 VL squared. So this is actually showing that this additional mass is ms over 3. So only 1/3 of the mass actually has to be put at the tip here to represent the mass, the full mass of the spring in the system, and have the same kinetic energy. You can do exactly the same for the bar interaction, where actually the displacement, you know that the static displacement is Fx over Ea. You assume again that the velocity is a linear and starting from 0 here and ending with v at position L. And by integration, you get 1/2 rho Al over 3 times VL squared. This is again the additional mass, and note that rho Al is the total mass of the bar, so it's again 1/3 of the mass of the bar interaction. Now it is not always 1/3, but in this sample example it is. Now let's discuss the limits of the approximation. So we have seen that if we have a mass hanging from a bar interaction, we can replace it by an equivalent stiffness, that is Ea over L, and the mass hanging from it. But we could also use a second model where we have an additional mass which is 1/3 of the mass of this bar, which has been neglected in the first model. Now, using finite elements, we can also compute the exact response. So first of all, let's look at the natural frequency. So if we assume that we have no additional mass, we have k is equal to E over L, and the mass is 100 kilo, and we end up with a natural frequency of 145.87 Hertz. If we use the additional mass in this case, you will find that you have 1 additional kilo compared to the 100 kilo. So it's quite negligible, and as you see, the natural frequency is very close. So when you plot the response of these two systems, you see that indeed you have a slight shift, but this is not very big when you look at the big picture of the natural frequency. Now for these models 1 and 2, we also added the exact solution which was computed with finite elements. And what you find in that, in the finite element model, of course we know that the continuous bar has an infinity of mode shapes, and so they come also into the picture. And you see that here we have one extra mode coming at that frequency. So if you are using the equivalent model of one-DOF system with equivalent mass and stiffness, it will be valid for frequencies which are smaller than 2000 Hertz. Let's assume now that the mass of the bar is multiplied by 10. Now the additional mass is not 1 kilo anymore, but 10 kilos, and so you see that there starts to be a significant difference between the natural frequencies, which is somehow visible here on the graph, and even more if you zoom. But what you also see is that because the mass of this bar is higher, its natural frequencies will be lower, and so they interact at much lower frequencies with the main dynamics of the system at low frequency. So in this case, you see now that the single degree of freedom hypothesis is not valid for frequencies higher than 500 Hz. As we saw, in some cases, the rigid elements in a structure can be replaced by a mass and the flexible elements by an equivalent stiffness. But there are some structures where it is not possible to make such an approximation. But as we will see, it is still possible to reduce the system to a 1 degree of freedom using the single mode approximation. Let's first look at the single mode approximation for continuous systems. So we consider a simply supported beam, for example, where we assume that the displacement is given by a function of time, psi of t, times f of x. Psi of t will be the displacement at a reference point somewhere on the beam, and f of x is the shape of the first mode shape of the beam. We assume that f at x equal to psi is equal to 1, so that psi of t is really the displacement of that point in time. So now we can use an energy approach. So the strain energy of a beam is given by this expression, where we replace W by psi of t times f of x, so that the psi of t comes out of the integral, and this integral here is given by k is defined as k tilde. So we see that in this case the strain energy will be written 1/2 k tilde times psi squared. So this is the equivalent stiffness. And in general, this equivalent stiffness can be given by some factor in front of EI over L cubed. For the kinetic energy, we have to integrate 1/2 times rho times the velocity squared, so that again we have the velocity at point psi that comes in front of the integral, and we express this integral term as an equivalent mass, so that the kinetic energy is 1/2 m tilde psi dot squared. This equivalent mass can be expressed as a factor times rho L, which is the total mass of the bar, the beam. Now we can also express the work that is done by the force applied to the system, which is in this integral form, and can be also written as an equivalent load times psi. This equivalent load can also be written as a coefficient in front of a distributed load P times the length. Now we end up with a system which is a single degree of freedom with equivalent mass m tilde, equivalent stiffness k tilde, and equivalent force P tilde. K is given by a factor times EI over L cube, and m tilde is given by a factor times rho L, and P a factor times PL. And these factors can be tabulated as a function of the boundary condition. So for example here, for a simply supported beam with a distributed load, you see that the stiffness factor is 48.7 and that the mass factor is 0.5. If you take this example of a beam where you have a load in the middle, we can see that then the k tilde is given by 48.7 times EI over L cube, and the equivalent mass is 0.5 times the mass of the bar. If we plot the response of the equivalent single degree of freedom system, we find the orange curve, and you see that if we use the full model, using for example either analytical expressions or a finite element model, you see that of course in the full model you have other modes at higher frequencies, so that the validity of this one-DOF approximation is here only approximately up to 70-80 Hz. We can use a very similar approach if the structure is modeled with finite elements. We have the mass, stiffness and damping matrices from which we can extract the mode shapes, and we will assume that the displacement is given by a single mode approximation with mode psi I in this case. Then we project the equations of motion into this single mode approximation, and we get a 1 degree of freedom system equation, so with the modal mass, modal damping and modal stiffness and modal forces. Assume that a force is applied at position xi on that beam. Then we know that x at that position is given by psi I at xi times zi of t. We also know that the fi is psi I of xi times f. So that we can just replace here the zi by x over psi I and the fi by psi I f, and then divide everything by psi I of xi, so that we end up with this equation here. So this equation projected on one mode shows that it is going to be the equation of a 1-DOF system where the degree of freedom is x, so the displacement at position xi, and we have an equivalent mass, an equivalent stiffness and an equivalent damping, but you see that there is a scaling factor psi I squared at xi that depends on the position. So basically you will have equivalent mass, stiffness and damping which depend on the position. So let's look at mode shapes of a building, for example. This is mode 1 of the building, mode 2 as we have already seen, mode 3, mode 4 and mode 5. And let's assume that we are going to reduce to 1 degree of freedom related to mode 1, where the position is given by this reference point. So what do we have to do? We have to compute mode shapes and natural frequency so that we have also the modal masses, and then we have to look at the shape of the mode at the reference point, which is here this point. And you see that if I take a point at a lower end here, this equivalent mass, stiffness and damping will change. So with a simple modal analysis on the finite element model, and by choosing a reference point, I can find equivalent mass, stiffness and damping to get an equivalent single degree of freedom system. If we compare the response again, you see that for a collocated transfer function, so we are looking at force applied here and displacement at the same location, you see that the orange curve has only one natural frequency because it's a 1-DOF system, whereas the full model shows clearly that there are more resonances, but this 1-DOF system, equivalent 1-DOF system, matches very well the response of the full model around the first natural frequency.
In this video, we have seen that whatever the complexity of a structure, it's always possible to reduce it to a single degree of freedom system approximation with an equivalent stiffness, mass and damping. But always keep in mind that this approximation is only valid in a given frequency band.